Hi everyone. Again, we continue our journey for making our data to talk, to speak to us, to inform us about some hidden information about the characteristics of the data and how to visualize the data, how to represent the data, how to give you some real and useful information, something you cannot see by your eyes. One of the most important topic in chemometrics and multivariate analysis is principal component analysis. Sometimes the variables used for making a prediction, especially for spectral data, you can find a correlation between variables. And of course, you cannot use variables that is already correlated. Correlation means they are the same. They have the same trend, even the same trend to grow together, and one to grow and another one to be declined, inverse relationship. You cannot use both parameters and both variables at the same time. You need to reduce the dimensionality. You need to reduce or to get rid of all of the correlated variables. One of the methods used for making this dimensionality reduction is principal component analysis. For example, if I have this data, and this data, as you see here, contains 4 variables used for making a discrimination or classification of 12 samples. So I have 12 samples, and each samples, as you see here, is recorded at different 4 variables or different 4 wavelengths. If you build a correlation matrix, you see here there is a correlation between 300 nanometer and 350 nanometer. Correlation coefficient is about 0.91, and this is not good to use both of them to make a prediction or to make a classification or discrimination. So you need to get rid of one of them. Okay, so the spectrum here is very simple because it contains only 4 variables, but our real spectral data could contain hundreds of variables, hundreds of wavelengths. That's why you need to get rid of all of the correlated variables and keep only the variables that are not correlated, or to convert these variables to another data space called principal components. Okay, let's go for a journey to know what is a principal component. If we have only 2 variables, considering for a problem, and this is the point between x1 and x2, for example, 2 variables here and 2 wavelengths. Of course, they are not correlated at all, but you can even replace these 2 variables and make a projection. We are trying to rotate this x and y components or coordinate and see which component is more representative for the data points that we have. The more representative line is the line that give us the less error between these lines and the data points. That means we have to make a projection. If we project this data, you can see minimum values of error between the data point and my line. So you need to make this kind of rotation, and each time you calculate the projection and to calculate the error, and the one that is give us the minimum error is the best one. And minimum error means it carry or can have a lot of variation, the maximum variation between all of your data. And if this BC1 is called the principal component, is BC1 that carry a lot of information, a lot of variation between the variables, the one that is really perpendicular to H1, to this principal component, will carry the next most variation between the data point. So the difference between the principal component here and the original variables, this is a linear combination. So we can convert the data variables to a new variables. It's called the principal component using the normal multilinear regressions that we have just seen before in our previous presentation. So BC1 carry the most significant variation, a lot of variation. And the next principal component, second principal component, carries the next largest variation. Don't forget, and then in BC1 accounts for the most of variation. The second is BC2, third is BC3, and so on and so on. But what happened if we have not only two variables, we have hundreds of variables? We need to think about this rotation and projection of your data to identify the principal component that capture the highest amount of variations between your data point. Okay. In mathematics, this calculations is called eigenanalysis, and the principal components is the eigenvectors. And eigenvectors comes from the covariance matrix of your data. So in general, the principal components is the eigenvector, or we can call it loadings, and the amount of variation is the eigenvalue. If we look at the examples that we have just seen in our last slides, this is 4 variables for 12 samples, and then this is a variation, and this is the percentage of variation. Using the principal component, here you have the eigenvalues. This is the eigenvalues, or the principal component eigenvalues, or the variation. Eigenvalues coming from principal components is variation, amount of variation. So principal component 1 captured 6.85 from 9.4, and the BC2 captured 1.4. As a percentage, as you see here, this principal component captured about 72% from this one, because this is 6.85 and this is 9.42. So this principal component 1 captured about 72% from the variation, and the second principal component captured about 15%, and the third principal component captured 9%, and so on and so on. And if you need a cumulative summation of this one, okay, you can see at the end we captured 100% of the variation. So if you summed all of these eigenvalues of all of this information, it should equal 9.42 as a variation. Okay, so if we look again to this calculation, here the coefficients mean is the column. This column contains the coefficients or the principal component, and these components could be used to convert the normal axis, the data that we have x1, x2, and x3 to principal component. Make a conversion, making this rotation to make a projection of your data. These coefficients of this column of principal components is called loadings, because it is the principal component or the coefficient used for make a projection. Okay, and these coefficients could be used as we see before to make a conversion between the x variables to another variables called PC1 or PC2. Okay, if you multiplied these parameters or these coefficients in the original data, you have in each sample you have something is called scores. And these scores, if you make a plot of these scores at the first principal components and second principal component, you can see how your data could be grouped, could be discriminated to 2 groups. For example, we have 2 distinct groups. One group contains these samples, and another group contains samples. Of course, using the previous information, we cannot make this kind of categorization or discrimination between the samples because it is not clear. That's why these principal components is called hidden variables or latent variables, because it gives us information about something could be hidden, is not able to see by your eyes. Okay, so BC1 and BC2, because it captured most of the variation and they make a projection for the data, can make this kind of discrimination, make a distinct limit and the threshold between 2 groups of data. Okay, so if you make a reclassification of your data to 2 groups based on in these categories, you can figure out something really interesting. For example, you can see here the first group has higher coefficient than the other group, okay? And another thing, this is contains lower value than the other one, and so on, okay? That's why we have this one, because here in the coefficient here, the coefficient of principal component is positive for the 300 and 350, and is negative at 300 and 400 and 450. That's why we can use principal component 1 and the principal component 2 for make this kind of distinction between these two groups of data, okay? As I told you, that's why principal component is called latent variables or hidden variables, because we cannot see in our normal variables. So in mathematical point of view, how we calculate these loadings and the scores. The angle between the suggested principal component and the original one is called the loading, okay? This is the angle. And then the scores of each sample is the distance between each principal component is called the scores, okay? So in general, we have the data, our data, X data is divided to two matrices. One is called loadings, related to the principal components, and another one is called scores. Scores make a map of the samples, and the components making a map of the variables or wavelengths. So you have the original data is divided to scores related to the samples, and loading related to the variables or the wavelengths. If we multiply this and consider there is some error, so we obtain the original data. For example, here, if you have this original, this X matrix of spectral data with 30 samples and 28 variables, this of course could be divided to scores and loading, or scores with 30 samples and number of variables or principal components, and loadings with the same samples but with 28 variables, and so on. If you multiply scores and loading and add the error, you obtain your original data. If you look to this analysis, this is the scores for this data, scores and loading. If you need to obtain this value using only one principal component, you need to multiply the scores of this one in this one, in the loading of this principal component, okay? But if you need to consider two principal components, you need to multiply this by this and then sum with this by this. As you see here, I can predict the original value using only two principal components instead of all variables, as you see here. What is the real number, the ideal number of principal component? How many numbers, how many principal components I can use in my analysis? Only 1, 2, 3, 4. It depends of calculation, what is called hotlings, okay? So you need to calculate the variation, amount of variation, and the principal component or summation of the coefficients and loadings of principal components less than 5%, for example, should be ignored, should be removed from analysis. For example, I have two examples here. These examples, we have here three principal components. After calculation of the hotlings and calculation of the variation here, I can see the cumulative variation here is less than 5%, so I consider only two variables because this is less than 5%. If you look to the hotlings and then the cumulative one or the percentage, so you can see this 1, 2, 3 principal component is not good enough because it is less than 5%. That's why I consider this example only for principal components. So 2 principal components are enough for this data, and the 4 principal components are enough in this data. But you can even make a graph between the number of principal component and the cumulative variation. If you see here at 4 principal component capture a lot of information about 90% of variation. So how to make a calculation of this principal component in Matlab, for example. So if you have this data and this data, you can make only very simple. Just put your data, okay, and then go to Matlab and write PCA. So I have the data, right in Matlab, I need PCA, and Matlab will give you these coefficients. So if you interested about seeing the principal components, scores, hotlink, variation, and cumulative variation, explain the variation, just write what you want and write PCA of the same data. From this situation and from this expression, you can obtain the scores and loading. If you multiply scores by loading, you obtain the original data. Very simple, very straightforward. But if you are interested also to see the variation or the explained variation, cumulative variation, the hotlinks, even you can visualize all of this data. It's really, really interesting to make this in Matlab and very straightforward. Hopefully, this presentation is very useful for you to give you an introduction about PCA and how to use to make a visualization of the data, to make projection of the data, and to make how to use it in a very simple way to make a discrimination of your data. Okay, see you.